All right, good morning, everybody. Yeah, I agree. I guess we're supposed to get more today and tomorrow, but uh, it snowed in Winnipeg. That's the big news. I wasn't in Winnipeg in '97. I also was not especially old in '97, but I don't really know if this one holds up. How we doing, everybody? Um, Happy Thursday. Class canceled for the people in person, but we're online. No snow days, no fun. You heard it from the administration first. If you're taking the morning off and watching this later, you have my blessing. If you're here now, you gotta stay. Them's the rules. Anyway, so I got this warm up question for you to think about. Give you a second to think about that. While you're thinking about that, let me go over some terminology we didn't get to yesterday because we were talking about some of the cooler stuff. So, we talked about way back at the beginning of the semester the difference between a finite and an infinite set. So if there's a bijection between a set A and a set 1, 2, all the way up to n, then we say A is finite, spelled correctly preferably. We say A is finite and the size of A is equal to n. Otherwise, A is infinite. This is review. Here's the new stuff. We learned last time that there are different kinds of infinity, and we're just going to focus on one of them. If there is a bijection between A and the integers, then we say A is countably infinite. And sometimes we don't want to distinguish between infinite and finite. What we want to distinguish between is countably infinite or finite versus a bigger infinity. So the word for that is countable. If A is finite or countably infinite, then A is countable. So now for every set, we can ask multiple questions. Is it finite or infinite? And then if it's infinite, is it countably infinite or a bigger infinite? If it's either finite or countably infinite, then we say it's countable. So here's some examples. So the set 1, 2, 3 up to 1,240. This is finite. Also countable. But it's not countably infinite. It's not infinite at all. Set 1, 2, 3, just going on forever, which is the same as saying the positive integers. This set is infinite and countable. We saw last time that there's a bijection between this set and the integers. And then the real numbers, we saw that these were infinite, but they are not countable. This makes sense? Finite, infinite, countably infinite? Questions there? Kind of. Yeah, I mean, it's new, but these are just terms for what we discussed last time. So hopefully what we talked about last time makes sense, but we'll do some more of it today. So what are we saying then about this set? It's a set of real numbers, but if you cube them, you get an integer. So the real numbers we know are not countable, but I'm not taking all the real numbers, I'm just taking some of them. And this subset I'm claiming is countable. I'm claiming I can find a bijection between this subset of the real numbers and the integers. Anybody have a bijection between those two sets? Let's call this set A, just to give it a name. I want a function that takes a number. It's a real number, it doesn't have to be an integer, but it takes a real number, and if I cube it, then I get an integer, and I want to turn it into an integer. What should I do with it? Floor or ceiling is a possibility. Floor or ceiling might get a little bit messy because I want to make sure it's a bijection. So I want to make sure it's injective, that it's one-to-one. Floor and ceiling, probably possible, but can be a little bit tricky. What do I know about this set of numbers? What's their special property? If I give you a random element of A, what's your first thought to do with it? Find the cube root, right idea, cube it. Yeah, right? Every element of A can be cubed. So what are some elements of A? Just as an example, we've got cubed root of 2 is an element of A. We've got -1 is an element of A. We also have integers, like 7 is an element of A. All of these are numbers where if I cube them, I get an integer. So let's look at the function f mapping A onto the integers. F of A equals A cubed. Let's prove that this function is a bijection. F is a bijection. So if it's a bijection, I've got to prove two things. I've got to prove one-to-one, and I've got to prove onto. So let's do, which is the same as injection and surjection. Let's do one-to-one. If I want to show a function's one-to-one, I pick two outputs, and I show they had to come from the same input. If f of a equals f of b, then a cubed is equal to b cubed. And unlike square roots, the cube function has an inverse, right? Square roots get a little bit messy because there's plus or minus involved. There's no plus or minus for cubed roots, right? Just like -1 cubed is -1 and 1 cubed is 1. They're not the same. So I can take cube roots to get a is equal to b. So that means if I got the same output, I actually started with the same input at the beginning. And now let's check onto. So f is 1, 2, 1. And now onto. For onto, I have to pick something in the integers. So let y be in the integers. What value should I plug into f to get out y? Cube root of y. Exactly right. The cubed root of y is an element of a, because if I take the cubed root of y and cube it, I get out y, which is an integer. So f of the cubed root of y is equal to y, and y is in the range of f. And then because y was arbitrary, I don't have to say by the law of universal generalization anymore. I can just say, as y was arbitrary, f is onto. And since f is 1-to-1 and onto, then f is a bijection. Okay. So our conclusion is then that this set A is countable. It's countably infinite, even. There's bijection between it and the integers. Does that make sense? How do we feel about that one? Feeling good? All right, at least one person's feeling good. We can keep going then. So I want to build up some intuition about these sets. Some rules that we have for how these infinite sets work. What was the domain on this one? The domain was the set A. Our inputs were functions that when you cube them, you get out an integer. That was the set I called A up here. It's a set of real numbers, but it's not every real number. It's real numbers with the special property that when you cube them, you get out an integer. So that works for integers. It also works for cubed roots. So here are some facts. That we have talked about, but suddenly come up in a new light. If f is a function from a to b is a bijection, and g is a function from b to c is a bijection, we talked about how g composed with f, that's a function that takes in a's, secretly turns them into b's, but we don't see it, and then outputs a c, is a bijection. What this means in the sense of our countably infinite sets is, even though I defined countably infinite as having a bijection with the integers, you can actually have a bijection with any countable set. So this means if A is a set, f from A to B is a bijection, and B is countably infinite, then A also has to be countably infinite. So the definition of countably infinite is that you have a bijection to the integers, but in reality you just need a bijection with any countable set, any countably infinite set, because B being countably infinite means, I'll write down a proof for this. Proof. Since B is countably infinite, there exists a bijection G from B to the integers. That's by the definition of countably infinite. And then G composed with F is a function from A to the integers. That's a bijection. Sorry, squeezing this in here. So sometimes it's useful to find a bijection to the positive integers. Or it's useful to find a bijection to pairs of integers. Or it's useful to find a bijection to the rational numbers. All of that we know is countably infinite, and so you just have to find any one of them. So let's make a quick list of things that we know are countably infinite. Countably infinite sets include, so we've seen the evens and the odds. Those both work. Also, the integers, obviously, that's by definition, but also the positive integers. And then we saw pairs of integers. That was the picture where we just drew the picture, where we spiraled outwards, and we hit every ordered pair of integers. And also the rational numbers. This was the one where we didn't actually find the bijection, but we showed that there was an injection and a surjection, and I claimed that that was good enough. And we just did this set of cubed roots, x in the real numbers, such that x cubed is a real number. These are the cubed roots. That's also a countably infinite set. And so far, our only uncountable set, that's an infinite set that's not countable, only uncountable set is the real numbers. So let me throw a couple of theorems up here. Should that be x cubed? Yes, I'm sorry. You're absolutely right. This should be x cubed is an element of the integers, not the real numbers. Otherwise, that's just the real numbers written in a fancy way. X cubed element of integers, yes. Yeah, it would not be true with the real numbers here, because the set of real numbers that when you cube them, you still get a real number is all of the real numbers. And we know that all of the real numbers is uncountable. Sorry about that. Definitely just a typo. Okay, so here are some theorems that I want to prove. Well, that I don't want to prove. I want to prove. I don't have the time to prove. Here are some theorems you should know that I don't have time to prove, but there are proofs in Grimaldi if you're really interested. So, theorem: if A is countably infinite, then so is A cross A. So we saw this for the integers. It's true for any countably infinite set. And you can sort of see how this goes. If there's a bijection from A to the integers, then there's a bijection from A cross A to the integers cross the integers. Just got to do a little bit of work to make that true. And then there's a bijection from here to here. And so we're countably infinite. So you can take cross products, you still stay infinite. Here's another theorem. If A is countably infinite, and B is a subset of A, one of two things is true. What are the two possibilities? Help me finish this theorem. What are the two possibilities? It's either finite or countably infinite. So then B is countable. Either countably infinite or finite. So think about if A is the integers, the evens are a subset of the integers that are countable. 1, 2, 3, 4 is a subset of the integers that are finite. But I can't take a countably infinite set and take a subset and become uncountable. That's not possible. If you take a subset, then you get smaller. Maybe you shrink from infinite to finite, or maybe you shrink from countable infinite to still countably infinite. But you can't go up in size. And now this last one is I think a really interesting one. If we had more time, I'd love to prove it and talk about it, but there is no bijection for any set A there's no bijection from A to the power set of A. Any set A. Doesn't matter if it's infinite, finite, uncountable. You can never go from a set to its power set. So this proof is going to look a lot like our diagonalization proof for the real numbers, where you change all the digits one by one, but a little bit more involved because you're dealing with sets. This tells us another uncountable set. So far we only have the real numbers, but what is another uncountable set? Power set of A, well, what's A in this case? Yeah, power set of the integers. As a corollary is like a theorem, except it's basically just using the theorem. Also, heavy debate on how to pronounce this word. Some people say corollary, like me. Other people say corollary. Some of those people are nice people. That's what I'll say. Corollary, the power set of the integers is uncountable. On an exam, you would pronounce it written. If you have an oral exam, I won't take off points for pronouncing it a different way. But also, how did you get an oral exam? What happened here? Must have a Toyota. Okay. One more thing I want to talk about here. So we've seen some subsets of the real numbers that are countably infinite. There are also subsets of the real numbers that are uncountable. I'll just keep going with my green theme. Theorem. The interval between 0 and 1 is uncountable. And this one I can actually prove. Proof. This is just like a really cool proof that I like. The idea is that I want to find a bijection between the real numbers and 0, 1. And I need a function where I can plug in any real number and I just get out an answer between 0 and 1. Or I could go the other way around, right? If there's a bijection from A to B, then there's also a bijection from B to A. So I could also find a bijection from 0, 1 into the real numbers. And the easiest way to do this is to use a trigonometric function, which is wild to me. So recall that inverse tangent is a function that the inputs for inverse tangent, you're only allowed to input a value between minus pi over 2 and pi over 2. And you get out, tangent is negative pi over 2 to pi over 2 gives you any real number. Exclude the endpoints. Inverse tangent is the one I want. Inverse tangent goes from the real numbers. Input any real number, output a value between minus any real number is an input. You get an output between minus pi over 2 and pi over 2. The arctangent function, the inverse tangent function, looks like this. Where this is, you've got asymptotes at pi over 2 and negative pi over 2. So the idea is that I'm going to squeeze and shift this up to 0, 1, and then fix the endpoints so that I can get the those two values. So in order to squeeze it, I'm going to do arctangent. I'm going to take the output of arctangent. I'm going to add minus pi over 2, and then I'm going to divide by pi. So if f is arctangent of x, this gives me a value between minus pi over 2 and pi over 2. Plus pi over 2, this gives me a value between 0 and pi. Divide by pi. This now gives me a value between 0 and 1. This is a bijection from the real numbers to 0, 1 without those endpoints. And so this is already uncountable. So the open interval from 0 to 1 is uncountable. And the open interval from 0 to 1 is a subset of the closed interval from 0 to 1. And remember, we have this theorem that says if you're countably infinite and you take a subset, that subset can't be uncountable. So the contrapositive of this statement, all the way back to the beginning of class, is if you have a set that's not countable, if you have an uncountable set that's a subset of another set, that set can't be countable. Might have to look at that one again later, but not doing anything too fancy there. So this gives us a nice list of countable, uncountable, and finite sets. Countable sets uncountable sets. Over here, we have things like the integers, the rationals, the non-negative integers, the positive integers, pairs of integers, finite sets. All of these things count as countable. And now uncountable sets, we have things like the real numbers, that's the big one. We also have the power set of the integers. And we have the interval 0, 1. How did I get f of x? I knew the answer. So I know that f of x plus a constant shifts the graph, and dividing by a constant squeezes the graph. So all I wanted to do was take this picture, shift it up. So instead of from minus pi over 2 to pi over 2, it was from 0 to pi. And then divide by pi, so that it would be from 0 to 1. There's some trigonometry going on here, right? I haven't proven that f is a bijection. I'm relying on some trig knowledge. But this is my proof. My proof is this f, which I came up with because it works. I'm using it because it's the right answer, kind of thing. So the one last thing I want to say is how weird it is that the numbers between 0 and 1 are uncountable. All of the integers are countable. Just the numbers between 0 and 1 are uncountable. Also, the rational numbers between 0 and 1, that's a subset. So the rational numbers between 0 and 1, those are countable. But all of the real numbers between 0 and 1, those are uncountable. If you go on and take a course called Real Analysis, you'll learn you can always find a rational number as close as you want to any irrational number. The rationals are dense in the reals, but the rationals are countable, the reals are uncountable. Infinities are really weird, is what I'm saying here. Welcome to the world of theoretical mathematics. Is the power set of any set of the sets on the countable list uncountable as well? Except for finite sets. The power set of a finite set is finite, just bigger. The power set of a countable set is uncountable. Really good question. Is it only 0 or 1, or does it apply to any interval? It applies to any interval. They don't even have to be consecutive integers. They don't even have to be integers. I can find a bijection from 0, 1 to a, b relatively easily. So here's, very quickly, f from 0, 1 to a comma b, as long as a is a smaller number than b. F of x is equal to b times x plus a over b is what I want. 0 to 1. So that goes from 0 to b, bx plus a, x, shoot, I'm trying to do this off the cuff, bx minus b over a over b. So now that'll give me bx minus a plus a. No, shouldn't have done this off the cuff. How do I get a comma b? Take input 0 to 1, stretch it to 0 to b minus a, and then I add a. Okay, so I want b minus a times x plus a. That's it. This is a bijection from 0, 1 to ab, from the interval 0, 1 to the interval ab. 0 gets mapped to a, 1 gets mapped to b minus a plus a is b. And so I can find a bijection from 0, 1 to any set that looks like this. So any interval, 0 to 1, 0 to 0.1, 0 to 0.000001, all of those are uncountable. Let's take our break here, come back, talk about relations, and we'll call it a day. But yeah, we'll take 2 minutes. We'll come back 9:14. Say. I guess while we're taking our break, for those sitting here or those watching later on YouTube, here's a thought to blow your mind. So we know that there's different infinities. There's countable and there's uncountable. Are those the only two? The answer is no. There are bigger infinities than uncountable. We just lump them all together. There are bigger infinities than the size of the reals, because there's no bijection from the reals to the power set of the reals. So countable is one infinity. Size of the reals is another infinity. Power set of the reals is another infinity. Okay, so we have at least 3 infinities. Now the question is, how many infinities do we have? And the answer is that we have infinite infinities. And then the next question is, okay, which infinite infinities do we have? And the answer to that question, you'll have to take set theory to learn, is that we have an infinite amount of infinities, and it's so infinite that it is itself not even an infinity. It's too big to be an infinity. Set theory is wacky. Crazy stuff going on there. It feels like the playground double infinity. Yeah. Take set theory, and you can win the name the bigger number game. I name infinity. Yeah, well, I named the power set of your infinity. Okay. Enough of that silliness. Let's go back to something more reasonable. Gather back together. Okay. We've talked about sets, where the only question was, are your elements in or out? And then we talked about graphs, which was, are your elements related or not? And then we talked about functions, which was how you turn some elements into other elements. And now our very last step in this progression is relations. So graphs are made up of sets. Functions are not really made up of graphs. They're really made up of sets. But functions are just a subset of this bigger concept, relations. And so relations are whether pairs of elements are related or not. So it's sort of whether relations are related or not, but pairs of elements related or not. So let me be more precise. Any subset of A cross B is a relation on A and B. So relations are all about ordered pairs. I'm going to take some of the ordered pairs of A cross B. Let's deal with an example to see why these are called relations. If I make the set A equal to 1, 2, 3, then I know the set A cross A. That's the set of all ordered pairs. So that's got 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Let's pick some relations on this set A cross A. So R1 is the set, it's a subset of these things. I'm going to pick 1, 2, 1, 3, and 2, 3. Why did I pick this relation? R1 is less than. It's the less than symbol on this set A cross A. It's the set of things where the first thing is less than the second thing. 1 is less than 2, 1 is less than 3, 2 is less than 3. Any one of these pairs where A is less than B is true is in my relation, and anything where it's not the case that A is less than B is not in my relation. So let me do another example. R2 is the set 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, and 3, 3. What is the name of this relation? This is less than or equal to. Right, these are all of the pairs in here where the first number is less than or equal to the second number. Okay, do another one. This time 1, 1, 2, 2, 3, 3. What relation is R3? Yeah, good. R3 is just equality. It's the set of values that are equal to one another. But relations can be more general. I can take 1, 2, 3, 2, and 2, 2. And we don't have a special name for this relationship. Right? There's no, it's just the second number is 2. That's the only way to describe this relation. But the theory of relations is going to encompass it. So the idea of relations is I'm just taking any subset of my pairs of values. That captures things like less than or equal to, and equal to. But it also captures more stuff that we don't necessarily have a name for. And it captures a broad range of things. This set 1, 2, 3, cross 1, 2, 3, hard to get into some of them, but we will see relations can cover lots of different things. They're a broad class. In particular, if f is a function from a to a, then the pairs a comma f of a form a relation. So I guess one possible name for R4 is the relation a comma f of a, where f of a is always equal to 2. R4 can be thought of as a comma f of a, where f of a is equal to 2, constant value 2. But relations are more than just functions, right? Because functions, every input has to have exactly one output. Every a has to show up exactly once. Here in R1, 1 shows up twice and 3 never shows up. Still a relation, just not a function. R4 is a function, or can be thought of as a function. So relations are this very general, quite abstract concept. And we still want to talk about some properties that relations can have. So first of all, if R is any relation, it's connected with a graph. Every relation is associated with a directed graph with vertex set A. So every relation that's a subset of A cross A is associated with a directed graph with vertex set A and an edge from B to C if B comma C is in the relation. So here's an example. R4 has the following directed graph associated with it. One comma 2 is in my relation, so I draw an arrow from 1 towards 2. 3 comma 2 is in my relation, so I draw an arrow from 3 towards 2. And 2 comma 2 is in my relation, so it gets a loop. these are directed graphs. Directed graphs are allowed to have loops. It's not just our simple graph, the graph we were working with before. So here's a problem for you to think about. What is the directed graph associated with greater than or equal to? So if A is the set 1, 2, 3, 4, draw the directed graph, which we usually abbreviate by digraph. This is directed graph. For greater than or equal to. Give you a second there. So I get 4 vertices. 1, 2, 3, 4. And I want to draw an arrow from B towards C if B is greater than or equal to C. So 1 is only greater than or equal to itself. 2 is greater than or equal to itself and greater than or equal to 1. 3 is greater than or equal to itself, and it's greater than or equal to 2, and it's greater than or equal to 1. 4 is greater than or equal to itself, and greater than or equal to 3, and greater than or equal to 2, and greater than or equal to 1. There's the directed graph associated with greater than or equal to on this set. So let's talk about some properties of reflections. This relation, every vertex has a loop. This relation, this vertex has a loop, but not every vertex has a loop. If every vertex has a loop, that relation is called reflexive. If for all A comma A is in my relation, then R is reflexive. Reflexive means everything is always related to itself. Here, 1 is related to 2, but 1's not related to itself. R4 is not reflexive. But every number is greater than or equal to itself. So greater than or equal to is reflexive. That's okay. Here's a property that greater than or equal to does not have. If for every A and B, if A and B is in R, then B comma A is in R, then R is symmetric. So neither of these two examples are symmetric. 2 points to 1, but 1 does not point back to 2. 1 points to 2, but 2 does not point back to 1. Neither of these examples are symmetric. What does the directed graph for a symmetric graph look like? What property does a symmetric graph have? If a relation is symmetric, yeah, right? Between any two vertices, I have two edges, one going each way, or I have none. That's also possible. So here's an example of a relation on 4 elements. And let's even go here. And maybe I'll add in a couple loops. This relation is symmetric because if there's an arrow from A to B, there's also an arrow from B back to A. R is symmetric. Is R reflexive? Not reflexive. Good. It has some loops, but there's not loops everywhere. Some elements are related to themselves, but other elements are not. Not quite the opposite of symmetric, but if we look at this relation, it's very not symmetric. There are no edges that go both ways. 2 points to one, and one does not point back. Right? It's possible that sometimes you have directions, arrows in both directions, and sometimes you don't. Then you're not quite symmetric, but you're not as non-symmetric as this. So if for every A and B, if there's an arrow from A to B, then there's not an arrow from B to A, then R is antisymmetric. So here, this relation is antisymmetric. Antisymmetric, not anti-Semitic. This is a perfectly fine relation. Please do not cancel it. Antisymmetric. Greater than or equal to is antisymmetric. My apologies. Close one. Cancel culture, run amok. Greater than or equal to. Cancelled. No, I don't want to get into any of that. That's a joke. Bad joke. Shouldn't have made it. Apologies. Okay. Reflexive, symmetric, antisymmetric. One last quality. Is transitive. Transitive's the hardest one to figure out just from the definition. If for every A, B, and C, A and B are related, and B and C are related, it means that A and C are related. Then R is transitive. Okay. What does this mean? It means if A is related to B and B is related to C, then A is related to C. Okay. So think about this in terms of greater than or equal to. if 4 is greater than or equal to 3 and 3 is greater than or equal to 2, then 4 also has to be greater than or equal to 2. Right, we have transitivity. If A is bigger than or equal to B, B is bigger than or equal to C, then A has to be bigger than or equal to C. Is this relationship transitive? We got a yes. So if I pick some elements, A, B, C, is A related to B? A is related to B because there's an arrow from A to B. Is B related to C? Yes, there's an arrow from B to C. But is A related to C? A is not related to C. There's no arrow there. So R is not transitive. So let's do some examples with this reflexive, symmetric, antisymmetric, and transitive. Like I said, relations are very broad. They can cover a wide range of things. So examples, depending on what your set is, can vary very wildly. So here's an example. A is the set of integers, and A comma B is in the relation. Sometimes we write this A, R, B, as if you replace R with a less than or equal to or an equal to sign, right? That would make sense. So A, R, B, A comma B is an element of R if A divides B. This is a relation. Sets of numbers where the first divides the second, that's a subset of integers. Is this relation reflexive? Is it symmetric? Is it antisymmetric? And is it transitive? What do we think? So what does reflexive mean in this case? Is it true that for every integer A divides A? Yes. So this relation is reflexive. Every number divides itself. Is it symmetric? If A divides B, does that mean that B divides A? No. Right? It is always true. A always divides A. No, it's not true that it's always symmetric, because A divides B does not mean that B divides A. Is it antisymmetric? Is it possible that A divides B and B also divides A? lost chat for a second. Internet's doing a thing. Antisymmetric. If A divides B, can B divide A? Right, this is antisymmetric, because I do need to be more careful about my definition of antisymmetric. I need to go back and adjust this, because if A divides B, B does not divide A unless what is true? Unless A is equal to B. And I should have included that in my definition of antisymmetric, so let me make sure I go back and add that. If A is related to B, then B is not related to A unless A is equal to B. That's fine. That's allowed. Antisymmetric does not rule out being reflexive. You're allowed to have loops. You don't need them, but you're allowed to have loops. You're just not allowed to have 2 cycles. You can't go from one to back. Okay. And the last question, is R transitive? Oh, interesting. I had not carefully considered B equals negative A. Yeah, I guess technically no. Ooh, forgot about that. I was thinking about, so let me change this. Let me cheat to make my answer right. Greater than or equal to 0. And that way I don't have to worry about negative numbers. But you're right, if I don't rule out negative numbers, then I guess it's not antisymmetric, because -2 divides 2 and 2 divides -2. Okay, is it transitive? If A divides B and B divides C, does A divide C? This one's a little bit harder to see, but I do think we did it back when we did divisibility. This one is transitive. If A divides B and B divides C, then B is equal to A times K, and C is equal to B times L, which is equal to A times K times L. So A does divide C. And we have a special name for these types of relations that are reflexive, antisymmetric, and transitive. If you are reflexive, antisymmetric, and transitive, then you are a partial order. If R is reflexive, antisymmetric, and transitive, it is a partial order. Partial order meaning you can put things in order from smallest to biggest. Maybe not perfectly, but you can say if one thing is smaller than another. Because you're antisymmetric, you can never have A smaller than B smaller than C, and then C actually smaller than A. You can show that that can't happen. If A is smaller than B, then B is bigger than A. And transitive assures that this works the way you want it to. If A is smaller than B and B is smaller than C, then A is smaller than C. Another type of order of relation we have is if R is reflexive, symmetric, not antisymmetric, but symmetric, and transitive, then it is an equivalence relation. equivalence relation. An equivalence relation tells you when things are equal. So as one last example, I know I'm 1 minute over, but just want to finish up with this one last example. If I give you this relation, where 1 and 4 are related to themselves and each other, and 2 is just related to itself, and 3 is just related to itself. This is an equivalence relation. And what I'm saying is that 2 is equal to itself, 3 is equal to itself, and 1 and 4 are both equal to themselves and each other. I'm splitting 4 up into the groups 1 and 4, 2, and 3. And what I'm basically doing is I'm looking at the set 1, 2, 3, 4, mod 3. 1 and 4 are the same mod 3, is what I'm saying. We'll talk more about modular arithmetic next week. Also more about relations next week. But I'm over time, so I'll stop here. Have a good weekend, everybody. Stay safe in all the snow.